Okay, you know how I keep saying that there's just a couple of fundamental things you need to know to do intelligent GIS work, and that one of them is understanding the differences between vector and raster data. And one of the reasons for that is because it totally affects the analysis that you do and the tools that you're going to use to work on your data. The way you build your models, the way that you approach the analysis is going to be constrained by or driven by the data types that you have to work with. So in this set of slides, we're going to talk through some of the basic tools that you use on vector data. And another word for vector analysis is geoprocessing. We're just processing geospatial data, but this is the vector set of tools. First, there are a lot of different ways to access tools. In ArcMap Desktop, you can use the toolbox, opens up a search window, or there's the toolbox and then there's the search window. This opens up where you can see all the tools organized within their different toolboxes. And then the search window allows you to just do, your traditional search. Here's the toolbox view. So the tools are kind of organized by, general categories of what they do. In ArcGIS Pro, same thing. Under the Analysis tab, there's a toolbox, and then there's shortcuts to ready-to-use tools, and then there's a geoprocessing window that's the same thing as the search window in ArcMap, where you can search for individual tools just using keywords. And there's the toolbox view. Okay, so first let's talk about proximity tools. But as I talk through these, I want you to think about data. Think about the landscapes that you're interested in. Think of your research questions and how you can apply these tools to your interests. And like usual, I'm going to go through these at breakneck speed because my goal isn't to explain all the inner workings of every single spatial analysis tool known to humankind, but instead I want to give you kind of a rough idea of some of the things that are possible and common in geospatial analysis to sort of unleash your creativity. So proximity tools. These are going to help us answer questions like, how close is this well to a landfill? Or do any roads pass within 1,000 meters of a stream? We could deal with protection issues. What's the shortest street network route from one location to another? Like I said, there's no magic to the way I'm presenting these tools. It's just the way they're organized in the toolbox, and it seems like as good an outline as any. So yeah, let's talk through some of these. These in polygons are similar to the Voronoi polygons that I talked about in week 1. These zones represent areas where any location within the polygon or the zone is the closest to the point that's in your input. So you'd be inputting a set of points. The output would be polygons that define where on the landscape, it identifies the closest proximate point. So anywhere in this green polygon, this point is the closest one. Okay, point density tools. You're going to use this very soon. The output is a raster, but the idea is this is a bunch of maritime aggression points, so piracy points, and we could calculate density from these points. You can weight it using a population field, and it's up to the user to define the search radius. When you look at the output, when you think about it being a raster output, the density is going to be driven by what area, what neighborhood you're looking in, and that's why that search radius is so important. So raster output, where the cell value equals the density of points within a certain neighborhood. All right, buffering. Buffer is pretty intuitive. It draws a ring around your features. It can be points, lines, and polygons that results in output. And you can have a single output or you can have multiple distance buffers. You can even get fancy and use a field in your attribute table that might have some value in it that defines the width of your buffers. Buffering in ArcGIS is, like I said, pretty straightforward. You set the buffer distance, but there are some options that you could consider, like whether it's a full buffer or just buffering one side of your feature. If your ends, if you want them to be rounded or flat, and dissolve type. So this is an undissolved, where each feature might overlap its buffer, and each buffer maintains its own shape, or you want the boundary between these two buffers from these features to be joined together, and you just end up with one big buffer around two proximate features. So here are some of the nuances for buffers that you should think about. If you have a lot of features, what happens if they overlap? So are you going to dissolve or not dissolve? If you're buffering a line, do you want the ends to be rounded or square? If you're buffering polygons, are you buffering inside or outside? So if this red line defines your polygon, this would be an external buffer and this would be an internal buffer. Do you want to include the original feature, or do you want it to act like an island? So if this is your original feature, this would be a buffer that's just creating a ring around but doesn't include the interior. And then a biggie is, are you using a projector geographic calculation? So are you using a Euclidean distance or a geodesic distance? And this shows the two differences. If you're working in a projection like this, the red is showing what a Euclidean buffer would look like, applying the projection, but a geodesic calculation you can see the distortion on the map, right? You can see that Greenland is bigger than Africa, which is clearly not true. So we have a bunch of distortion going on here. The geodesic is taking that into consideration. And so the blue buffers in real life are all the same size, whereas the red is allowing the projection to distort the area of your buffer. All right, space-time tools. We talked about these in our initial map Blitz. Some interesting stuff here, and I guess I just bring it up as a reminder in case anyone's interested in trying this for their final project. Near tool. So let's just say you're curious about how a tool works. Know that you get lots of clues in the tool itself. So it, again, tells you this tool modifies the input data, so it's not going to ask you to name an output file. And if you have questions, click on these question marks. The question marks are going to pop up links to tool descriptions. So the near analysis, it gives you a little summary, it gives you hyperlinks so you can pursue it through GIS Pro help pages, and then it almost always gives you an illustration to show you how it's going to work. The same goes for all your inputs. They usually have little question marks by them, so it defines the inputs for you and helps you figure out how to set these things. All right, overlay tools. Oh, well, I should probably tell you what the near tool does. The near tool, like let's just say you have sage-grouse nesting sites, and you have another point file with telephone poles, or if you have a line file with roads in it. The near tool is going to output an attribute table where each lek has a distance to the nearest pole, so a distance value, and an angle to tell you the direction to the nearest feature. So 2 input features. All right, that was kind of proximity in a nutshell. Here's overlay tools. Overlay tools help us overlap, join, or combine different data layers in a bunch of different ways. So how two data layers overlap each other. Vector overlays, it's just very easy to picture. 2 polygons overlaid, and then the differing operations that you can apply to that overlap. Which parts of the polygons are going to be kept, which parts are going to be discarded, and what happens to the attributes that are associated with each one of these layers. So an intersect is an exclusive function, meaning the output is going to be smaller than either of the inputs. So the intersect outputs the overlapping area, the places that are coincident between the 2 data sets. So if this is input 1 and the lines indicate some kind of boundary, like this is 4 different features. Here's input 2 with 2 different features, 2 different areas. It's like a Boolean and. So where this exists and this exists, and that's what I mean by an exclusive function. The output does keep in mind, it considers all the internal features, and that's why you get all these multiples. So this line represents this set of feature breaks, and then these funky lines are represented here. But you don't see any of the areas that are beyond where both exist. Both attributes are carried forward into the output shapefile, so it maintains everything. This little sliver would show these green attributes and this feature's attributes, if that makes sense. How it looks in ArcGIS Pro is pretty straightforward. Again, if you click on the help, it shows you a little picture of what to expect. You have a yellow input and you have these blue outputs, and this is, or inputs, and you get this as an output. All right. Union is the opposite. It's an inclusive function or a Boolean or. So wherever these features exist or these features exist. So you're going to get the largest extent of both areas. Both sets of attributes are carried forward, so it's going to include all the feature breaks like you see, and you would just get everything printed to the output attribute table. Same thing. In ArcGIS Pro, use the question mark to get an idea of what it looks like, and pretty straightforward. Okay, erasing. Erasing is where you can use a feature to cut your input. Erasing doesn't include attributes, so it's going to completely ignore the attributes associated with your erase feature. It's just basically a cookie cutter, but in this case it's like a negative cookie cutter. You've got a bunch of input polygons. Your erase feature is going to stamp out or get rid of stuff that you don't want. The opposite of that is a clip, and the clip isn't kept in the the overlay files. I don't know why, but it's also just a cookie cutter, but it's the opposite. So if you have a bunch of input, you use your clip feature. It ignores any internal divisions. It doesn't take the attributes into consideration. It just literally stamps out and keeps everything inside your feature. So the opposite. A couple of quick problems with overlays. Very often data is created at different scales or different sources, and the boundaries won't be exactly coincident. And so if you do some kind of intersect or union, you'll end up with a bunch of little tiny slivers of polygons that are created when the two data sets don't completely match up. You do have to deal with that. It's a problem. Sometimes you can sort your results and just delete all the features that are smaller than a certain size. You can set tolerances if you're working with, well, there's a lot of different, without getting into the weeds, you just have to address these sliver polygons. And if anyone's curious, we can talk about this more, and we can go over some of the details of how to do that. But it's honestly a quick Google search. There are probably 10 different methods for dealing with the slivers, either in the up front in the construction, where you can kind of set some topology rules in a geodatabase, or using snapping if you're doing digitizing and forcing your lines to be coincident. There are a lot of different ways to address this, but know that this is a common problem, and you can, explode data sets up to tens of thousands of features because, 9,000 of them are these tiny little mistakes. Okay, I'm going to stop here to keep these short, and then we'll pick up again and finish with some extract tools.